Hi, I'm Becky Weems. I'm one of the science development coordinators here with STEMscopes. Going to walk you through an activity you can do at home. This is with our properties of light scope. This is available for free for you. If you can manipulate the FET on your own, just following the handout that's attached. If you don't have the ability to do it, watch the video. I'll manipulate it, but then you can still answer the questions and follow along. Okay. So first, we're going to investigate how light paths travel between different transparent materials. I'm going to start by hitting the intro, changing this bottom material from water to air. Okay. We're going to turn on the laser, add our protractor, and then align this to 60 degrees. Okay. So from right now, it's moving from air to air, so it's not changing material. I want you to describe the path this light ray is traveling and make sure to cite evidence from the protractor. So for here, I want to see a number value added. Go ahead and pause and fill this out. All right, so clearly what we're looking for here is straight line. So so this light went straight, and our evidence here is that the protractor went from 60 degrees as the input. Output was still at a 60-degree angle, so that stayed the same. Now we're going to change the material from air to water. Okay. Now with water, it is still transparent. So remember, transparent just means allowing light to pass through. A lot of times people think of them as clear things, but this is a different medium or material than the air. So this medium is the water. We still have a 60-degree angle as the input, but now I want you to describe the path of the light as it moves from air to water. Again, make sure to cite that evidence from the protractor. Very good. At this point, I would hope you would see that it doesn't go straight anymore. Now the angle bends, specifically at a 40-degree angle, looks like. Okay. Now for step 9, going to change the medium again, this time going to glass. Okay. Once again, I want you to describe the path of the light as it moves from the air through the glass this time, and cite that evidence from the protractor. Very good. Now, this one bends. It does not travel straight. It bends more similarly to the water. But why we wanted you to mark that evidence is that it doesn't bend to the same degree. So for this, it looks like now the angle is at a 35-degree angle. For question 11, you now have 3 different observations that you've recorded. Right? Based on these 3 simulations you just explored, I want you to describe the path light travels as it is transmitted between transparent materials. Really challenge yourself here. I want you to come up with a similarity between all 3 as well as the differences. And you can go ahead and pause the video if you need to. All right. So first, it's important to note that regardless of transparent material, all 3 transparent materials allowed the light to shine through them. Right? If this was an opaque material, that's where you would see that stoppage and the light would not pass. So all 3 had light moving. Now where they differ is that when it was the same medium or that same material with the air, the light continued in a perfectly straight path. The water and glass, though, was a different medium, a different transparent material, and when the light shined through that, as soon as it hit that medium, there was a shift and the light bent. Now we're going to move to frequency of light. To do this, I'm going to go to the More Tools simulation at the bottom. Okay. I'm going to turn on the laser, change this from ray to wave. I'm going to take out this time tool, and this is going to, in real time, show you the wavelength. I'm going to make this a little smaller so that we can focus on the simulation. That's a little easier to see. Now, you notice this number here is the length of the wavelength. It's in nanometers because they're small. Okay. Now, what kind of wave is being shown here? This is a transverse wave model. That's what it is. It's a type of transverse wave. Now I'm going to manipulate this light color. Okay. I'm going to take it to this far end of the spectrum. Did your wavelength increase or decrease? Now I'm going to slowly move to the left. Okay. And as that's going on, you should see that the numbers are changing. So we can now answer these first two questions. Which has the shortest wavelength? Which color has the shortest wavelength? And then answer B, which has the longest wavelength? So violet, this purple color, this should be the one that you noted as your shortest wavelength. The longest is the red. Now we're going to talk about wavelength and frequency. So wavelength, you have the number here. Frequency is determined by how many times a wavelength, so wavelength you measure actually from the tops of these peaks. So from crest to crest, that's how they generate the length. Frequency is how many times a wave passes through something in a period of time. So now I'm going to start with the longest wavelength because we're at the red and just focus on this time. Watch what happens to the frequency as I move it down. Okay. Now I'll go the other way compared to that. Answer C and D now. Determine what you think the relationship is between the violet color wavelength and frequency, and then the red. Take a pause, and then we'll come back and discuss. All right. So we already determined that the shortest wavelength was the violet. The frequency, though, was the highest. So whenever the lowest wavelength was equated to the highest frequency. The red color you should have seen was exactly the opposite. It has the longest, largest wavelength, but the smallest, the shortest frequency, which makes sense. If you have to move a very long way, you're only going to be able to get not as many through as if you're only moving a very short distance. Okay? Quick and fast, you're going to get more wavelengths in the same period of time. Okay? Now, that moves us into question E. The concepts of wavelength and frequency are closely related, but have slightly different meanings. So this is where I would want you to put your definition of wavelength and frequency here. So wavelength, the measurement, I would expect to see from peak to peak or from crest to crest. The distance, it's how you measure how long a wave is. Frequency, the amount of times. We want to put a time indicator onto our frequency definitions. Okay. F, I just talked about. So wavelength and frequency. There is a relationship. Would you say that this is a direct, a positive relationship, or an indirect? So for here, this relationship, there's a strong one, but there's an inverse relationship, meaning that as one goes up, the other goes down. So wavelength wavelength and frequency are inversely related. How do wavelength and frequency of the colors change as you move? And this is when you just talk about, describe what is happening to the wavelength of the visible light spectrum. So the wavelength increases as you move from violet to red, or if you're reporting the other way, the wavelength decreases as you move from red to violet. Now this last part, it just is an open piece for you. I said you are allowed to access this for free online. If you log into the site, you can click on the prisms and do an entire investigation on your own. But that is as much as I have for you today. Thanks for logging in, and I hope you enjoyed the video. Stay safe.